Alright, so for whatever reason, the last video didn't record successfully, and I finished the exam, so I'm just gonna do a summary anyway. It's probably more convenient for rapid fireness. So here's the second linear algebra exam in rapid succession. So the first question, consider M, this matrix, find the inverse with Gauss-Jordan elimination. So what we're gonna do, you set up the matrix here, you augment it with the identity matrix, and you convert this into, well, the identity matrix. Whatever's going to be on this side is going to be your inverse. So I just do all that, and I get this, and that's me checking it online to make sure I did it right. Next one, find the intersection points, if any, for the lines. So you've got these two lines. Let's see if I can zoom in for you. So I just take these and put them in parametric form. I use a different parameter for the second one because, well, I want it that way. So we've got XYZ, XYZ, and I set all those up, so I'm just reading it across this way. I get those, set them equal to each other because, like, this one's both equal to X. So then what I do is I just set it up so I've got all my variables on one side and scalars on the other, and then I take this, put this into a matrix, and augment it with this side here, and I solve for those. So basically what I'm doing is I'm looking to see if Q is equal to T and the lines intersect at that point. But I get an inconsistent system here because I've got 0 of both of these and it's somehow equal to 42, which is a no-go. So the lines don't intersect in that case when you get an inconsistent system like that. Alright, next one, consider this matrix, find the basis for column A. So what I do is I take that matrix, set it up, employ Gaussian elimination again, and I just go all the way. I don't have to go full blown. I can just get it to where I have pivots and it's in row echelon form, and the column vectors that have pivots are going to form the basis for my column space, except I'm not taking this 1 0 0 0 1, for example. I'm just taking this, going back to my original, and see these three are circled, so those form the basis for my column space. Now if I want to find the basis for the row space, what I'm going to do is I'm going to take that same thing and I'm going to reduce it down even more. So I keep going until I've got zeros above and below all my pivots, and then I get this. So basically these three rows are going to be the basis for my row space. So you can see it spans these guys. And for the null space, what you do is you take this matrix, you set up your variables, and you plug them in. So you can see there's two parameters here, x3 and x4. These guys are going to be parameters, so I picked t and q because my s's look like 5s. And yeah, so then I just solve for all of these and set up these two matrices, or these two vectors, and those two are going to comprise my null space. Another fun fact is that the null space, I've got 2 in there, and then my column space I've got 3. That's got to be the rank of the matrix, I guess. What is it? There's a theorem here somewhere. Rank theorem. If A is an m by n matrix, then the rank of A plus the nullity of A equals n. So rank of A is how many column vectors I have comprising my column space, and the nullity is how many vectors I have comprising my null space. That has got to be equal to the number of columns of my matrix. So that's a quick way to know if you mess something up. Alright, next. This is a linear transformation question. So consider the linear function f. It goes from R2 to R2 defined by this transformation here. So it wants me to find the standard matrix for this transformation. So what I do is I take different columns of the identity matrix. So I would start with this, right? And then I just look at this column here. This is a I hat. and this one here is j hat. So I take I hat and I plug it in to this guy, and then I solve, and I get a vector here, and this one here I get this vector. So what's happening to I hat is it's going from 1 0 to 5 4. What's happening to j hat is going from 0 1 2 minus 1 3. Anyway, I take those two, plug it in, that's my transformation. Next one. Find the standard matrix representation for the linear transformation L, which takes r squared to r squared and projects vectors onto the line. Y equals -1/2 x. So I just grabbed a couple values here. I said at x equals 2, y equals -1, just to get a direction vector for this line. And then what I do is I take I hat and I project it onto that direction vector, and I get this. And then I take j hat and do the same thing, project it onto that direction vector, and I get this. So the standard matrix for this guy is this column, and this one is this column. So that's it. Now this one I wasn't too sure on. I don't know that I understand this question, so I really need to ask my teacher about it today, which is the first thing I'm going to do when I get to school, because he has office hours when I arrive. So for now, this is what I did. I'm assuming they want me to apply this transformation and then apply this one, and they want it done as like a regular matrix. So I was just saying, like, if I take this notation doesn't make any sense. I'm just going to put F and L here because they're about the previous question. You see, you got L here and you got F here. So for F, I said F was this guy and L was this guy. So I just rewrote them down here. I think what you're doing is you're taking X and you're applying this transformation. I think you're adding them together, because I think there's like a where is it here in my handout? Thing that I made. That guy, the top one. I think that's what's going on. Now, if I'm wrong, then I'm wrong, but this is my rationale. So if I do it with I hat, my y's are 0s and my x's are 1s, and so I just take this plus this when x is 1, and I get that. And I do the same thing for the other guy and get that. And I said that was it. So I don't know if that's what this means. I'm not familiar with that notation, so I don't know why it's on there, but anyway, it's just something I missed. Alright, so the next one is basically just some complex arithmetic. So they give you two complex numbers here, and then they get you to compute various things. So the first one they want 2 times the conjugate of w minus z plus 5i. So the conjugate of w, you just need to remember, is if it's minus 4 minus I, it's going to be minus 4 plus I. So that's what I did here, and it's just basic arithmetic. You go ahead and get this answer. The next one is 3z minus w, the magnitude of that, or the modulus they call it. So you're going to just take that out, 3 times z, so you just distribute that 3, minus w, so you distribute that negative sign. You get this, you get that. This is just the magnitude of it, so you take 11 squared and 8 squared, take the square root, or minus 11 or minus 8, whatever. And that's your answer. I didn't simplify it any more than that, because I don't care to. W times, well, that's basically, if you know how to do this one, then you're good to go on this one, because you're just using a complex conjugate again. It's just a notation. It's just checking that you know what it means. So that's cool. I get that. And w divided by z, well, this is w, that's z, but dividing complex numbers, just multiply by the conjugate in a form of 1. But if you notice, this times this is the same thing I computed here. So I already had that answer, so I just chucked it up top. And then this, when you multiply it out, will give you 25 plus 9 because it's 5 squared plus 3 squared, and then you get this answer. This one here, okay, this one's hairy. I wish he gave us the fourth root of 16, or the fourth root of z. So he gives us z is minus 16i, so that guy is sitting down here. And if you want the fifth root of it, basically what you do is you take the fifth root of the magnitude of this. So if this, like, let's say it was pointing up here, well, you'd have to get the magnitude of that, which would be this and that added together, their squares added together and square rooted. But this one's actually kind of easy because, you know, all you gotta do is just take that. I put it in the calculator just to see roughly what it was. So you get, it's the fifth root of 16, which is 1.74. I don't have any other way to simplify that that I know of. So basically you're just going to end up with this guy, and because it's the fifth root, you're just going to divide that, divide this, whatever, if I could draw it properly. There's my pentagram. I just do that to make it easier. So basically you're going to have 5 unique solutions to that. So how you do that is you just remember that z equals r times cosine theta plus I sine theta. So the general form just for z itself, the regular one, is 16, because that's the magnitude of it, because the magnitude is just the modulus of z. So it's 16 squared, square rooted. And then the angle I've got is the angle from the positive x-axis, so that's going to be this one here. So that's going to be theta. So theta is 3 pi over 2. And then I just put the general form, but because I'm taking the fifth root, I'm going to divide this angle by 5. And remember that, like, you're going to have plus 2 pi k, because there's an infinite amount of solutions, right? So there's some ambiguity there. So I just picked strategic values of k. I picked k equals 0, 1, 2, 3, 4. And I just computed the angles here and got those. This one reduces, actually, I saw later. So, but anyway, it's fine to just leave it like this. Anyway, you're going to have the end result. He wants it in a plus bi form, so it's going to be the fifth root of 16 cosine 3 pi over 10 plus I times this guy times that. And you're just going to have, they're all going to look exactly the same, except you're just going to have a different angle in there. So when you graph it, it looks kind of like this. They all happen to be separated by 4 pi over 10 or 2 pi over 5. But yeah, so that's going to be what your graph looks like. Alright, so the next one is decide if v, this vector, is in the span of these three. Easy enough, I guess. You just take this, put it into a matrix, and augment it with this, just to see if v is a linear combination of these guys. So you reduce it down, and you get an inconsistent system. 0 is not equal to minus 7 no matter what you multiply it by. So v is not in the span. So this guy, you can't combine any of these in any way, shape, or form to form this guy. Next one, decide if this set is independent. Well, you just take this, put it in a matrix, reduce it down. If you have a pivot in each row, then you're good. It's it's going to be independent, but in this case I only managed to get 2 pivots out of 3 that I needed, so it's dependent. Next one, you get some matrices. They're all given here, and they just want you to compute various things. So 7a minus r, well, since a and r are both 2 by 2s, I can do subtraction or addition. This 7's a scalar, so I can just distribute that among all of these guys and basically come into this. So you just carry this over, right? And then yeah, you'll get this matrix here. AC, well, I kind of highlighted here. This is a 2 by 2 and this is a 2 by 3. If these two guys, if the number of columns in your first one equal the number of rows in your second one, then you can compute it, and the resulting size of your matrix will be these outer ones. So it'll have the same number of rows as your first one and the same number of columns as your second one. So you're going to do this guy times that guy plus this guy times that guy, and that's going to be your first entry. Your second entry is going to be this guy, then this guy, this guy, then this guy, and that's 3 plus 8. So you just keep going, you fill it up, and then so you're just going here, these two, then these two, these two, then these two, these two, then these two, and then you just go down to your next row and complete the same process until you get this. 3C transpose, well, here's C transpose. You literally just exchange your columns for rows. So your first column becomes your first row in this order. And 3 times that is you just distribute this 3 into the whole thing, and then you get that. B times C, well, B is a 2 by 1 and C is a 2 by 3, so a 2 by 1 and a 2 by 3. Well, that and that don't agree. You can't compute that one. So that's the little trick one. B times B transpose. You just take B and then take its transpose by just flipping it over. So you're going to have your columns become your rows over here. And so you just do this times this, this times this. And then you're going to get this matrix here. And then B transpose B is this one. See, we get, these are 1 by 1 here, so I get a 2 by 2 at this, but this one is a 1 by 2 and a 2 by 1, so you're only going to get a 1 by 1 matrix, this guy. And this is, so that's where I left off in the last video, and then I did a video this morning, but it didn't finish recording or whatever. So anyway, this one, the generic formula is this. So R e to the I theta. Well, I'm just going to take this. He wants it in this form, a plus bi. So what I'm going to do is I'm going to take e, I'm going to split this up. So I'm going to take e squared divided by e to the I, and that's going to give me e squared. And remember, e the I, there's a theta here, but theta is 1 in that case, right? Because there's nothing multiplying it. So, and also the radius is 1 because there's just a 1 sitting out here. So it's r cosine theta minus, or plus I sine theta. So that's what this is going to be. This is a complex number, so I can't really, to divide by it is kind of weird. So what I'm going to do is I'm just going to take that, multiply it by the conjugate. Well, when you do that, you get cosine squared plus sine squared. That's going to be 1. And you just distribute this e squared. So that's your final answer. All right, next one. Let M be a 2 by 4 matrix. So this guy. Entries labeled M, I, J. So I is your row, are your rows, and J are your columns. Write down the matrix M. So what you're going to do, I just do this to keep things straight. So I, for this one, this is the formula given. So I'm going to take 2 times 1 minus 1 squared. So that'd be 2 minus 1, right? And you're going to continue that on for all of these entries. So like this one here is 2 times 2 minus 2 times 2 minus 4 squared. You're going to keep going with that. I don't know. Maybe I think I might have messed that up. Did I? Yeah, okay, hold on. 2 times 2 is 4 minus 3 squared, so that's minus 9. Okay, that's why. Yeah, I think what I did is I put a 2 in here and cubed it or something. I don't know. Who knows? It was early. All right, so that's how you're gonna compute this. This is just a. These are quick answer questions anyway. State the basis theorem. That's the basis theorem. It's on the. It's on the sheet here. Theorems I need to memorize. I hate when they just make you memorize stuff. It drives me nuts. But there's the basis theorem right here. So let S be a subspace of Rn, then any two bases for S have the same number of vectors. I guess that makes sense. I mean, if I have R2, well, I'm going to need two vectors to describe that, even if they're not the I and J unit vectors. If there's something else, then that should be able to describe it. Alright, so, and then this one here, this is literally just copied from the, I had to look this up. So this one here, it used to say W here, and I just took the white marker and whited out the, oh, look, I even wrote W. That's funny. Alright, so, what this is saying is, state the definition of a set of vectors S to be a subspace. Well, the subspace has to have vectors in it, so it can't be empty. Cool. If X, if the vector X is in S and Y is in S, then their combinations are also in S. And you take an alpha scalar. It's saying this is it's in the complex numbers, which comprises all the numbers except for like quaternions and stuff. So all the reals are in here. So A is just a scalar, and if you take A times X, that's also going to be in this subspace as well. So anyway, I just wrote this again. Look, I wrote W again. Anyway, all right. So find the elementary matrix E that corresponds to this row operation. So I look at this and I see, okay, well, what row operation did they do to turn this guy into this one? So I said it was negative 1/2 row 2 plus row 3, right? Because we're just getting rid of this 1. So you take 2 multiplied by negative 1/2, that becomes negative 1. You add it to 1, it becomes 0. And you take this one, and that becomes a 3. And then a 3 becomes a 2. So I just take that row operation and apply it to the identity matrix, and that will be an elementary matrix. So I take negative 1/2 of row 2 and add it to row 3, so I get this guy. So that's going to be my elementary matrix. That's not too bad. Write down the inverse of this matrix, so I just called it A, and I just did it. This is exactly like the very first question, right? But just a lot quicker. So yeah, knowing it's one of these, I mean, I guess I could just look at it and know, but I always take the long way home, you know. So that's the way you do that one. Anyway, so that's midterm number 2. Pretty close to perfect, except for this guy, because I wasn't really sure what the question was asking. So in my page. Stuff to ask Fimbo, that's number 1. Anyway, see you on the next video. Bye.